Day of this International School of Life Science and Technologies. It's a pleasure to start this day, this long day, with 3 talks in the morning, and in the afternoon we are going to have a round table, okay, with 5 panelists, okay, 5 panelists. So with this round table, we are going to close the sub-area of communications in the core of this international school of this year. To start the morning, we have another very important talk, because the topic and because the speaker. About the speaker, I will tell just very few additional words, additional to the words as I said yesterday. I must say that Professor Pendry is not only a scientist, he is one person, one scientist that in addition is with very high compromise with the college. So he was the head of the department, he was the dean of the faculty, and he managed many things in the Institute of Physics. So this task, of course, is always for the rest of the people. So top-level scientists, but in addition, working for colleagues. But what I would like to mention, just to give the word to Professor Pendry, is the fact that in 2014, maybe you remember that 6 people received Nobel Prizes in topics very close correlate with light. 6 people, probably the first time in the history. From these 6 people, 3 was in the area of emission of light. Professor Nakamura, that was last year here, and other colleagues in Japan. But the other 3 received the Nobel Prize because he contributed in order to remove what up to this time was like a stone, to remove the resolution of things. Up to this moment, maybe you remember that you only was able to resolve when the distance between the object was more or less in the area of the wavelength, as Professor Pendry told yesterday. And in this way appears the A number and so on. But I must say that Professor Pendry could be one of these Nobel Prizes, because he did incredible good job in this area, and in fact, just in this year, he received the Cowley Prize from the Norwegian Academy of Science and Letters in nanoscience. And the reason for what he received this prize was textually for transformative contributions to the field of nano-optics that have broken long-held belief about the limitations in the resolution limits of the optical microscopy and imaging. And the other recipient of this prize was Stefan Hell. And Stefan Hell was one of the Nobel Prize this year. So we have in this room a very important scientist worldwide. And he is going to speak now just in these topics, light in nanoscience, because new phenomena appears when you work in super small dimension. So, Professor Pendry, thank you very much for your great contributions to the advance of knowledge, and it's your time. Everyone would like to hear your voice. Thank you.
Well, thank you very much for that introduction. Today I want to continue the theme I introduced yesterday and apply it to how we might concentrate light into a volume of a nanometer or so. And we're going to use the techniques of metamaterials and transformation optics to do this. But before that, I should like to make acknowledgements of my team, particularly Paloma, who together with Emmanuel and Fan Yang has contributed to nearly all of the work that I'm going to speak about today. So, yes, I need the clicker, don't I? Yes, will this do the work? Oh. Ah, good, thank you. Just need to turn it on. So, a brief recap about yesterday's talk. I introduced the subject of metamaterials and the importance of structure in determining the properties of materials. And here we see an example of a silver mirror, nearly 100% refracting throughout the visible and into the ultraviolet. You make silver nanoparticles, as in a photographic plate, and the reflection coefficient and the transmission coefficient both go down. It's very, very strongly absorbing material over a broadband region. And intriguingly enough, I hope to be able to show you today that this has a connection with string theory. It's rather tenuous, but it does. So, metamaterials, properties determined by the internal structure, and if that structure is on a scale much less than the wavelength of light, then we can continue to use epsilon and mu in the usual way. And that's the big difference from photonic crystals, which actually have their structure on the same scale as the wavelength of light and derive their properties from diffraction of light. Metamaterials are not like that. Their properties are due to nanoscopic events, such as resonances, but they can be described by epsilon and mu. And that's a simplification in the design process, because you can design your structure in the usual way and ask what epsilon and mu are, and then in a separate process, engineer the metamaterial. And you can get very highly novel properties, as I spoke about yesterday. And we're going to talk about many things today, but in particular, we're going to make a terahertz broadband absorber using these techniques. So we need this new tool of transformation optics. The traditional tool of Snell's law is not adequate on a scale less than the wavelength, because rays don't exist on that scale. But electric and magnetic fields, which are the ingredient of Maxwell's equations, then these will provide the intuitive ingredients that we're going to use to design the structures we're talking about, and use transformation optics to bridge that gap. Oops. Okay, so that's just repeating what I said yesterday. And to remind you, this is the, you can use transformation optics, and from the transformation, you can extract the values of epsilon mu formally, algebraically, or there is an intuitive way of doing it, which is just to recognize that if you compress some space like this, then epsilon and mu in this direction are reduced, and epsilon mu in that direction are increased by the amount of the squashing, okay? And there's a special case of this, of conformal transformations. Conformal transformations mean transformations in which the shape of objects is preserved, but their size is changed. So if I'm going to do a conformal transformation, I have to press this way and this way. And what that means is that you decrease, increase, you decrease, increase. Are you with me? Decrease, increase. What we end up with is that in that plane of this square transformation, you get back to where you started from. So conformal transformations in 2 dimensions do not alter epsilon or mu. And that has been known for a long time and been used to design capacitors in difficult situations. It was, in fact, conformal transformations that were used to design the aerofoil. I think that was the first use of them in the mid-19th century. And we're going to use those, which will be applicable to 2-dimensional transformations. We can do the full thing, but it's particularly simple in that case, and so I'm going to exploit that to explain a lot of things that I can do, and then we can do them exactly later on. So one has to go backwards before it can go forward. Now, an ingredient of the talk today will be these objects called surface plasmons. Now, metals are metallic, conduct, because the electrons in metals are free. In fact, it's often referred to as the electron sea. And just like a real sea, the electron sea can have waves on its surface, and these waves are called surface plasmons. And metals are also characterized by the nature of the electrical permittivity, which below the plasma frequency is negative. So the plasma frequency is typically near the UV, and as you go down to lower and lower frequencies, epsilon becomes more and more negative, and if it were not for the absorption, it would become infinitely negative at 0 frequency. And it's this negativity which is going to give the super resolution properties I'll talk about today. If you remember yesterday, the formula for a perfect lens involved both epsilon and mu being negative. However, there's a let-out clause there, because if you want to have a negative mu at optical frequencies, then you can whistle for it, because there's very little magnetic response at optical frequencies. But the let-out clause is that if you're on a very, very small length scale, then you can neglect mu. And the reason for that is in an electromagnetic wave, an electric field turns into a magnetic field, turns into an electric field. And the length scale on which it does this is the wavelength, which is a few hundred nanometers. Now, if the distances on which you're working are just a few tens of nanometers, and all your sources are electrical, which they are in optics, then you never go far enough for your electric field to turn into a magnetic field. And therefore, you don't need the negative mu if you stay on very tiny dimensions. So that's the let-out clause, and it enables us to use metals to make what I call the poor man's perfect lens. And we're going to see how to design those today. So This is a diagram of the dispersion of the surface plasmon. It's a wave, so it has a wave vector. Very short wavelengths, large wave vectors. It's asymptotic to the surface plasmon frequency, which is the bulk plasma frequency divided by the square root of 2, typically. And as you go to longer and longer wavelengths, it collides with the light line and is asymptotic to the light line at 0 frequency, 0 wave vector. So I'm going to make the simplest singular transformation that I can. So this talk is going to be about singular transformations, and that's how we're going to harvest light. So despite the arrow going this way, I start off with a system which consists of a waveguide bounded by 2 slabs of silver. And inside the wavelength, I have a source, which might be an atom emitting some light. And the light, in this particular waveguide, is captured by the surface plasmons, which exist on the surface of silver. And by the way, these surface plasmons have a very high density of states compared with free light. And therefore, any atom there which is in the vicinity of the surface plasmon gives nearly all its light to the surface plasmons. And the surface plasmons in this waveguide system carry their energy to plus and minus infinity. They take infinitely long to get to plus and minus infinity. And this is a beautifully simple system. You can calculate its properties analytically, and its spectrum can be calculated analytically as well. And now I'm going to make an inversion. So let me I'm going to use complex numbers, so x plus iy, x and y. And then I'm going to make an inversion, which is taking points at infinity to the origin and points at the origin to infinity. Okay? And if I do that, then infinity becomes the origin, and all points in between these planes turn into cylinders. So this system here, through this singular transformation, is transformed from an infinite system to a finite system with this singular point, which is where the 2 cylinders touch. And just as this system here takes light from the origin and sends it to infinity, this system here takes light, which in this transformed system is at infinity. It harvests it here. This bit acts like an antenna, and it sends it to the origin. And as it, hello. And as it travels there, it goes more and more slowly. And just like cars on a motorway, when they go more slowly, they become more close together, become more dense. And in the case of this light, the energy becomes more densely packed and concentrated, and if you like, focused at this point. So this is an accumulation point of energy. The light never gets there. It's a bit like a black hole in that the light never bounces back, but it's not quite a black hole. But there is another interesting thing about this the system, and it's this, that we start with a system which has translational symmetry. And so you can describe the spectrum of the system in terms of a block wave vector. It has a wave vector. But this system has very little symmetry. It has a couple of mirror planes, and that's it. And yet, its spectrum is the same as this, because all we've done is transform this from here to here, and the solutions of this guy are inherited here. And still, we can describe it by a block wave vector. And this is what we call hidden symmetry. Now, you can make many, many transformations of this guy here into all sorts of structures, some singular, some not. But they will all have the same spectrum, whether or not they have the same symmetry. So we can understand systems which, this system previously when people wanted to calculate it, they had to expand on a computer in many cylindrical harmonics, about 100, because it's very singular and very difficult to calculate. But the whole thing can be calculated analytically. So that's an example, a very simple example of a singular system. Back, and then forwards and forwards, right. But what I want to do is to talk about surfaces rather than particles. And so let me show you how I do that. So let me start with this system here, which is a cylindrical system. And again, I can, because it's got cylindrical symmetry, I can calculate its property. So here's the silver, some dielectric or vacuum, and then I do a transformation which is a log. So I'm going to call log of the radius the y direction, and I'm going to call the angle around here, that's going to be the x direction. So as I go round in angle through the metal, I go along here, and as I go along the radius, I go along in this direction here. So a log opens out these two cylinders into an infinite surface. And then we can actually describe any metasurface or grating or whatever you like to call it in terms of a conformal transformation. So I can make a transformation which is essentially a Fourier transformation in angle of the shape of this inner guy here. And if the new coordinate is this power series in a complex number z, then I can generate an arbitrary, almost arbitrary shape. They're not quite arbitrary. There are some things you can't do. And then I can do my log transformation again, only now because this surface is not smooth, I'm going to get this saggy surface here, and I get an infinite grating. So you can describe almost any grating in terms of a conformal transformation. And I'm going to play with a very simple transformation in which instead of taking a log with this as the origin, when I go to a flat surface, I first do an inversion about this point here, and then I get two concentric cylinders again, but they're not concentric. They have different centers. And now if I do the log about this point here, one surface remains flat, and the other surface is this wavy shape here. And this simple series of transformations we can exploit. If you put them all together, it looks like this weird thing. But here is the shape of the grating as a function of this offset parameter here. So the more offset you make this, the more wobbly the grating is. And it's characterized by this number here. And all you need to know about that is W. When W is big, it's a very wiggly grating. And when W is small, it's really rather a smooth grating. So you can go between the two. And if you then say, OK, I'm going to calculate in the electrostatic limit, this is what you get. And you can do this analytically. And here is the dispersion of that grating. So the interesting thing is that this grating here is related to a flat surface. And if you confine yourself to the case where the solutions are continuous round here, which essentially is the center of the zone here, then this grating inherits the problem of this, the properties of this at the center of the Brillouin zone. So you see that in this dispersion relation here, in that here at the center, at the zone boundary, you have a grating which has a massive splitting of the dispersion here, and here at the origin, you have zero splitting. It's as if the grating didn't exist for k equals 0. And those are the states which you try to couple to when you have light normally incident on the surface, which of course has k parallel equal to 0. So a very curious second instance of transformation optics. Now that's calculating the electrostatic limit, quasi-static limit. You can do it properly using transformation optics again, and this is the analytic theory compared with COMSOL, and of course it agrees. Why shouldn't it? But the complication is that now you have a light line in the problem, and when the surface states of the grating cross the light line, they acquire a finite lifetime. In other words, they can radiate into the vacuum. And this is the profile of that particular grating. Now, one thing that you can think about is to say, well, these surface plasmons, they're coupled to light, yes, but also they have another role, and that is the surface tension of the metal. And this comes about because when you have a mode with frequency omega, it's never empty. The minimum energy it can have is a half h bar omega from quantum mechanics. It's the 0-point energy of the mode. So all these modes must be populated with a half h bar omega, and that's the energy of the surface, which is mainly due to surface plasmons, or at least they make a very large contribution. And the other thing about the grating is that it starts when there's no grating there with a surface plasmon here, and then you have this splitting here. And it's characteristic of splittings in optics that whatever the perturbation you introduce, it's almost always the case that you have two modes either side of the grating, and this lower mode goes down more than this upper mode goes up. And so as far as the surface plasmon is concerned, you reduce the 0-point energy of these modes, the net 0-point energy, because you're pushing this one down more than that goes up. And that would imply that there's some forces trying to make a grating on the surface. Of course, the forces trying to stop that happening, which are the elastic forces of the bulk solid. Nevertheless, it is true that all the noble metals have surfaces which are reconstructed. So here's a scanning tunneling microscopy image of a gold 100 surface. You can see the gold atoms there. There's a weak period in this direction, which is 28 atom period, but the key period is this five-fold, 5 atoms reconstruction here. And it may be that these surface plasmons have a role to play in that. We don't know. We're looking at that at the moment. There are many other examples of reconstructions in surfaces. For example, in high TC, there's a theory of what's called stripes, which are charge density waves on the surface. And again, it may be that the 0-point energy has a role to play there. So interesting things from gratings. Now, a very interesting example of surface plasmons is in graphene. Graphene is a semi-metal because it has 0 density of states at the Fermi energy if it's undoped. But it is very easy to dope it, which you can do by simply putting a charged plate of metal near it. And if it's a positive charge, it will suck electrons into the graphene and so dope it. And once it has some free electrons, the graphene then supports surface plasmons. But there's an unfortunate rule which says, well, fortunate or unfortunate, is that if the surface is completely flat, then you can't couple external radiation to the plasmons. And so you have to have a grating there before you can couple anything into it. But this is easy to do with graphene, and there are people in Barcelona, Frank Coppens particularly, who can make gratings in graphene, couple external terahertz radiation, and so probe the properties of the graphene. So using those theories I've told you about, here is the dispersion in graphene, this is the undoped graphene, uniformly doped, sorry, and this is the graphene with a grating in it, compared with the COMSOL calculations. And these surface plasmons in graphene have a very short wavelength relative to the terahertz radiation, which is externally incident and exciting them. Very short wavelengths. Typically 1 micron. So here's a calculation of, due to Paloma and Matthias, which shows graphene absorbing terahertz radiation. And here's the frequency of the terahertz radiation in electron volts. And the transmittance is pretty high until you satisfy the conservation rule for momentum parallel to the surface. Then you can couple to the graphene plasmons, and suddenly you get almost 100% absorption of the terahertz radiation. I think this is quite remarkable, because this is a sheet of 1 atom thick, and the terahertz radiation is essentially being captured by that sheet. So what Paloma was keen to do was to maximize this absorption here. And it's an interesting problem, because what you have to do is to couple the terahertz radiation into the graphene, into the surface plasmons, and the surface plasmons then dissipate the energy of the radiation as heat. Now, you might think that the stronger you couple the terahertz radiation, the greater the absorption would be, but it's not true, because having coupled the radiation into the graphene, you've got to leave it there long enough for the absorption to take place. And if you couple in strongly, then you'll couple out strongly as well. And so if it will go in quickly, it will come out quickly, and there won't be time for absorb. So it's the Goldilocks thing again. Or put in engineering terms, you have to match the impedance of the load to the impedance of the generator. So you've got to get that grating just right to maximize the absorption. And so that's just what Paloma's doing here. And this is W, telling you how wiggly the grating is. And you can see that these blue and green curves are the ones that are doing the best job. And the absorption peaks at different frequencies according to which of these peaks you're looking at. Sorry, at different modulation strengths. So, for example, for this first peak here, you tune the modulation strength measured by this parameter W, and here you see it's at its best. And then increasing the modulation doesn't help. The radiation is escaping, and it's a different frequency because the lifetime of each of these states is different. And so you can think of using this as a switch, because since the graphene has been doped by this DC electrostatic trick of putting some electrical charge near it, you can take that charge away. And actually, I'm told that you can switch these gratings on and off at gigahertz frequencies. So terahertz radiation can be switched by a tunable graphene grating at gigahertz rates. And some people claim it can be done even faster than that. So that's quite an interesting application which might come. So these are just ordinary gratings I've been talking about, but I now want to introduce this business of singular transformations, just as I did in that first one-dimensional example. So the absorption for these non-singular gratings takes place at a very specific frequency. And so if you have a specific angle of incidence, that defines the frequency of the surface plasmon with that wave vector parallel to the surface. And so unless your frequency is equal to that surface plasmon frequency, then you won't get any absorption. And so the absorption is, of this 2D system is characterized by a series of isolated peaks. But I'm going to show you that you can, in fact, make a broadband absorber by making a singular surface. And singular surfaces are typically gratings in which you have a sharp edge, or you have a finite-sized material in which you have the two sides touching at one point, and they are defined by not two parameters, they're defined by three parameters. And this is reminiscent of what the particle theorists sometimes speak about. So I have conversations with my friends who do work on string theory, and maybe you do too. And maybe you've heard that when they're trying to explain their esoteric mathematics to you, they say, well, it's a theory in 12 dimensions. And you say, what? 12 dimensions? I know about 4. What are these other 8 you're talking about? Oh, well, they say, they're rolled up. They're compacted. You can't see them. It's OK. And I go away mystified. But what I want to show you is that you can, in fact, in an ordinary, well, not so ordinary, but in these singular systems, you can produce examples of a compacted dimension. So I'm going to show you how you can make a surface which is two-dimensional to all appearances, but in fact is characterized not by two quantum numbers, kx and ky, but by 3 quantum numbers, kx, ky, and k hidden. So here goes. So that's just saying again what I've said here. If you're interested to look at it further, this is reported in, I think this is the December science paper, and this is work I've done in Paloma, Yu Liu, now a professor in Singapore, and Emmanuel, one of my current students. So how do we do that? OK, I hope you can bear with me this dance through the complex plane. But what we start with is a system which is clearly three-dimensional. So this is a series of slabs of, let's say, silver, separated by dielectric. It has 2 dimensions which you can see, and it has a 3rd dimension, which is the depth into the screen. And then I'm going to say, make a transformation to a complex coordinate z, which is exponential z prime, which is exponential z. And this takes points at x equals minus infinity. Exponential minus infinity is 0. So minus infinity goes to the origin. And the y-coordinate, exponential y turns into an angle here. And so round and round I go, silver dielectric, silver dielectric, silver dielectric, silver dielectric, silver dielectric. And plus infinity, exponential plus infinity is an even bigger plus infinity. So what we get here is a knife edge, or a wedge, or whatever you like to call it. So I've compressed 1 infinity to the origin, but I still have another infinity lurking there. To get rid of that, I do an inversion about this point here, which is remote from this infinity I've compressed here, so I don't want to uncompress it, so I just leave that alone. So I do an inversion about this point. So this point, which is close to the inversion point, now is far away. So that will be this point here. And then points at infinity go to the origin, which is here. And lines in between go to arcs of circles. So I get this lens-shaped object in which this singularity comes from minus infinity, and this singularity comes from plus infinity. OK, so I've captured the infinities, made two singularities, and now I've got to go back to a surface. So I then do this log exponential thing again, and so I go round in angle here, and the angle is the y coordinate, and the radius, log of the radius, is this coordinate here. So if I'm near the origin, log of 0 is minus infinity, and as I come away from the origin and go around, eventually I start cutting through this guy here, and so I make this grating, and these two singular points survive, and all these angles, because it's conformal transformation, are preserved. So I get this object here, and I contend now that the excitations of this object, which have the same spectrum as this guy here, these excitations are two dimensions in nature, because they're confined to the surface. They extend out of the surface as well, because I'm not fooled about with the dimension out of the surface. And this third dimension here, which is the x1, has been squished into these singularities, alternately plus and minus infinity as you go across this surface here. So this surface here is characterized by three wave vectors. And you can calculate those analytically if you're interested in things like that. So let's see, this is the dispersion as a function of the kx, the hidden dimension, just a normal, fairly dull dispersion relationship about the surface plasma frequency. And then you can throw in another of the dimensions if you like, and you can get the dispersion surfaces. So all seems well. And if you look at the modes of the grating, then not surprisingly, at this singularity, which has a compression, you compress the modes which previously went on to plus infinity. You compress them into this point here. And as you look at the phase of the mode, it goes into wild oscillation at this point here, at the same time, a huge amplitude. So if a wave is trying to cross the surface, it approaches this point here, it slows down, its intensity increases, and it actually never gets past that point because it goes slower and slower and slower, just as if it were going to infinity, which it is. Of course, it's conformally transformed. Now, knife edges aren't easy to make on metals because metals have huge surface tension, and what they want is a nice, smooth curve. They don't like knife edges. That's why your knife goes blunt. So to actually observe these singularities, we go back to this example I showed you before, and to the example of graphene, and introduce another singularity. So I think, as I mentioned, you can, if you make an inversion about this point here, then you get to this shape of surface here, and then back to an ordinary grating. But what we can do is to make these two transform cylinders so eccentric that these points touch, okay? And then in the grating, these two surfaces would touch here. And that act of touching of two curves is another singularity. And here we go. So if we let these, this is a notional period of a grating. It doesn't really have a grating, so it's a flat surface. And then we can transform it to here. And if this period goes to infinity, then that's equivalent to pushing these two guys close together like that. Okay, so these 2 points here rush off to infinity. These stay where they are, but at the same time, these two are pushed into contact. And Emmanuel has, oh yes, this is how you do it with periodically doping the graphene. Only now you dope it strongly here, but you allow the doping to go to 0 at the intervening points. Easier said than done, but that's the idea. And then you get something very similar to the knife edge. You get, at this point here, you get the modes oscillating wildly and going very, very intense. It's an interesting thing about, you can think of this as a waveguide, and you're probably familiar with ordinary waveguides which have perfect metal boundaries. But this, although it's made of metal, this is a metal with a negative epsilon, which is very different from a perfectly conducting metal. So an ordinary waveguide, if you taper it, make it more and more narrow, eventually the cutoff will come up in frequency, and at some stage the tapering will be such that there'll be a cutoff point, and the wave will go to a longer and longer wavelength, and then eventually infinitely long wavelength, and at that point it bounces back. So tapered waveguides made of perfect metals will reflect a wave. But in contrast to that, if you have a tapered waveguide where the surfaces are excuse me, made of negative epsilon, the surface plasmons interact with one another, and they go to lower and lower frequencies as the surfaces get closer to shorter and shorter wavelengths. So actually, when you make a grating like this, which is made of essentially negative epsilon material, and you taper it, you actually suck things into that tapering, which is most counterintuitive. But here's a calculation which shows that that really happens. As a wave approaches this grating, it's just sucked into it and never to return. So that's the way you can make another source of singularity. And here are Emmanuel's calculations of the spectrum of that grating. So what he's doing is making the grating approach the singularity gradually. So here's the doping profile. In A, the doping profile doesn't go to 0 at the point where we're going to make it singular eventually. In B, you're getting close. And in C, you're almost there, but not quite. And so here's Emmanuel's theory. And you see that you get a series of discrete absorption peaks because it's not singular, just as we saw before. But you push further towards the singularity, and these peaks crowd in. By the way, the red dots are the COMSOL simulations. So this is just to confirm that our conformal transformations do indeed generate the correct solutions. In fact, singular structures are very, very hard to calculate in COMSOL. COMSOL is a wonderful set of codes, but some things it has problems in handling, and singularities are one of those things. So COMSOL gives up the ghost at this point, and so we soldier on alone with the analytic theory for C, which is almost singular. And you can see what's happening, that if you put in a little bit of loss, as you can see here, red has more loss than blue, then eventually these peaks all merge together into a continuum absorption. And that's because there's no longer this strong selection rule at the surface that you can come in at any angle you want, and there's always a frequency, a mode at that frequency that you're tuned to, And what you're doing is selecting the hidden wave vector. So hidden wave vectors have singular surfaces. So when you look at an old-fashioned photographic negative, just think you're doing string theory. You're looking at a compacted dimension. I tell my string theorist friends that with tongue-in-cheek, and they look just as baffled as I do when they tell me their theories. Yes, so singular surfaces are black. Okay, so one more thing before I finish, and that is that these singular surfaces, you can think of them as a metamaterial. So if you're just shining terahertz radiation on this graphene grating, and the wavelength of the terahertz radiation is very much larger than that of these excitations, which it is, then that's the condition for a metamaterial. And so you can do the metamaterial trick and replace this grating on the surface by a thin layer of a given impedance. So here, what we show is the impedance of, no, this is the conductivity, sorry, of flat graphene, which is the blue. This is the imaginary part, which is the reactive part, inductive part rather, and the lossy part relative to the impedance of free space. And you can see that graphene itself is fairly loss-free. It's got an imaginary conductivity and therefore is quite free of loss. But if you put this grating on the surface and you ask, what is the effective conductivity of this singular grating, then you get a reversal of the situation. You get this line here. And of course, once you match the impedance of free space, this is going to be a very good absorber indeed, which it is. And it absorbs the maximum, which is half of the incident radiation at this point here. There's also some inductance, and there's a long tail going off into way beyond. So that's been a whistle-stop tour through some of the things you can do in optics and in terahertz using the tricks of transformation optics. So what we've done is we can make graphene almost black to terahertz radiation over a broad spectrum. The way we do this is to make a singular structure on the surface, and this is an example of a metasurface because the structure happens to be much less than the wavelength of terahertz radiation. And these singular structures, by undoing the singularity through a singular transformation, you can relate them to non-singular structures, waveguides, which have an extra dimension which is compacted into the singularity. So we believe that that can be realized through the doping of graphene, and we're now inviting tenders from experimentalists to see if they can actually do that for us. But I believe we do have an example in the case of the silver blacks and the gold blacks. So I've left a little time for questions if you have any for me. Thank you for your attention.
Thank you, Professor Pendry. I think that you show the way for many young people in future work. So you can find a lot of possibilities to work in this area because we expect to get very good contributions, and young people are key issue for this kind of topics. Okay. So now it's time for questions. Please. Any question? That one, please. Yeah.
Thank you for your quiet, interesting presentation. It was really Nice. I have some question. Maybe I didn't quite get the concept.
Okay.
I found that with using transformation optic, we changed the ideal situation to what we would like to have,
Yeah.
Especially regarding the issue of epsilon and mu. So we have black wave in the situation of regular photonic crystal and Brillouin zone, and we can deal with the black propagation and black mode. However, in this structure, we want to design a specific condition of epsilon and mu, and we do not have any idea about in the final stage how we can go through this transformation from what we want to what we shall do. You know, it's a quite.
I think I see. Can I use this curve as an example? Okay. So the desired effect here was to go from a discrete spectrum to a continuous absorption spectrum. I mean, there are many situations where you might want a black body. So the technique for doing that was to identify a singularity. Now, that's where you have the choice. So I showed you two ways of making a continuous spectrum. The first one involved making things into a knife edge. And I said, well, maybe that's a good way of explaining the singularity, but knife edges are difficult to make. So we had to look for another singularity, which perhaps was easier to do, and that was the graphene one, where you push this density down here. And then the next thing to do is having got a continuous absorption spectrum here, you then tune the other parameters, which are here. So there are lots of parameters in this transformation here. And once more, the challenge is to match the impedance of that structure that you get, regardless of the metamaterial, so that its impedance matches that of free space. So all the way you're looking at these handles you have in the transformation. First of all, you have a discrete choice of what sort of singularity you're going to make. There are lots of them you can think of. And secondly, to fine-tune the parameters so that when you come to make the metamaterial, that this guy here, the conductivity, the impedance is matched the impedance of free space. So this is normalized to free space. So if you make this equal to 1, that's the best you can do in terms of an absorber. And okay, it's not perfect, but it's not bad. Imagine something 1 atom thick absorbing half of everything that's incident upon it. Not bad.
Any other question?
Sorry, say again, please. Yeah.
Stability of this metasurface will be because it's 1 atom thick, so like...
Stability. Yeah. Well, if you know about graphene, it's the wonder material. It's incredibly strong in the plane, and people can pick this stuff up on, what do they use? Scotch tape, I think, don't they? So they have you seen the Guine paper on graphene? First of all, he takes a pencil with graphite in it, and then he puts some Scotch tape on it, and then he looks at the Scotch tape and says, yes, we've got, this one's 2 layers, don't want that. And, I can see under the microscope that this is a single layer of graphene. Of course, there are more fancy ways of making it these days, but you can certainly, it's very robust. It doesn't tear easily. Yeah.
Any other question? Yeah.
Considering how this was made, it seems like basically graphene and maybe other two-dimensional materials could be used as canvases for creating all kinds of plasmonic surfaces in a much easier way than maybe patterning a metal surface. Is that correct?
Yes, it's other ways of patterning graphene are to cut holes in it, but that's not switchable. And of course, that's the way you have to do with things like silver. You have to make a grating and then you're stuck with it. And the beauty of graphene is that it's switchable. It's terahertz, which terahertz people like, but if you want to do optics, you have to think about metal gratings such as silver. And we're currently wondering whether we really can make these knife edges in silver or whether we can get a good approximation to them that would do the job. We don't know yet.
Okay, another additional question. Yeah.
Thank you very much for your talk. I was amazed about that. Have you ever tried, for example, making a metasurface with another two-dimensional material?
Yeah, like people are looking at things like molyslip, molybdenum disulfide, and actually they were making, when I was a student in the laboratory where I worked, they were making single layers of molybdenum disulfide. That's a layer material, molybdenum sandwiched between two sulfur layers, and it's a van der Waals material, so you can cleave it easily. So people are looking at these. The way you dope them is to put an alkali metal, such as sodium, potassium, or whatever, near them, and the sodium and potassium, the free electrons in them like to screen the van der Waals forces very much, and the molybdenum disulfide exfoliates, which means to say it suddenly expands. It's a very exothermic reaction, and the metal goes in, and it makes a monolayer of metal, and the electrons there makes up as plasmons. So yes, people do look at other two-dimensional materials. You don't get these as a monolayer. It tends to be a stack of layers, which makes it much more complicated to analyze. But they actually also show these charge density waves, and for many years people have looked at these charge density waves in molybdenum disulfide, and there's a whole series of dichalcogenides, as they're called, with sulfur, selenium, and all those things, transition metals. So yes, lots of two-dimensional materials. And the last time I heard Andre Geim talk, he'd got fed up of working on graphene, and he was working on these dichalcogenides.